Hello everyone. Today we are going to discuss next periodic property, that is ionization energy. So in the last video we have discussed the atomic radius in detail. So and the trends in groups and in periods. Now today we are going to discuss another periodic property that is very much important, that is ionization energy. So what is this ionization energy? I will tell you with in detail. So first, what is the definition? So the amount of energy required to remove an electron from a outermost shell of a neutral gaseous atom. Neutral gaseous atom. So what from this what we can understand? So what is this ionization energy? So the amount of energy which is required, that means we are putting that much amount of energy to remove an electron from outermost shell. We are removing electron from which shell? Outermost shell or valence shell of very much important neutral gaseous atom. We are removing electron from neutral gaseous atom. That means if an atom is in solid state, it has to be converted into gaseous state. So to remove electron from its outermost shell. Are you getting the point? So in this case, so we can say if this is nucleus, so there are number of shells. Let's consider this is what the outermost shell. So the electron which is present in the outermost shell, to remove one electron from this outermost shell, so we have to give ionization energy. That means we have to give the energy so that electron will be removed from the outermost shell. Because we know that the nucleus is holding the revolving electrons with its nuclear force of attraction, so that to remove the electron from the neutral gaseous atom, so we have to apply energy. So that energy which we are applying to remove this electron, that energy is called as what? Ionization energy. Like we can say, let's take an element M, it is there. So we are removing electron from this. So for removing this electron, we have to apply energy. So when we have given energy to this a metal or an element, so what is going to happen? We are removing this electron, and by removing this electron, this it will form or it will become cation or positive ion. Are you getting my point? So the amount of energy which you have given is called ionization energy. So this is what called first ionization energy. Why it is called first ionization energy? Because we have given it to remove first electron from the neutral gaseous atom. This is becoming what? A cation, or is also can be written as unipositive ion. Unipositive ion. But when it comes to, if you want to again remove one more electron from this unipositive ion, if you want to remove one more electron, so again you have to provide energy. That energy called as second ionization energy, because you are removing another electron from unipositive ion. Now it is becoming what? M2 plus. So if you wants to remove one more electron from this double positive ion, so what we can write? Again you have to remove one more electron. Again you have to supply energy, that is third ionization energy. It will become M3 plus. It keeps on going on, so that if we keep on removing electrons, so we have to keep on giving energy. So the next question comes, as we have discussed yesterday, the size of the positive cation, or the size of the cation, the size of cation is smaller than its neutral atom. Its neutral atom. So from this, what we can identify the size of cation. That means once you have removed electron, it is forming what? Cation. Unipositive ion or are what? They are cations. They are forming cations. So in this case, what is happening? The size of cation is becoming smaller. Yesterday I told you the reason, because once one electron is removed, once the electron is removed from the outermost shell of a neutral gaseous atom, the number of protons will be more than number of electrons. When the number of protons are more than number of electrons, what is going to happen? You are going to observe So the nuclear force of attraction is going to increases, or the effective nuclear charge is going to increases. So this nucleus will hold these revolving electrons with much more force as compared to its neutral atom. So now what is going to happen? So the size of cation is what? Smaller, so that effective nuclear charge increases. Effective nuclear charge increases. When this effective nuclear charge is increasing, when this effective nuclear charge is increasing, what is going to happen? The nucleus is holding the revolving electrons with much more force of attraction. So due to this much more force of attraction, what is going to happen? So to remove electron from this unipositive ion or from this cation, again you want to remove electron, so you have to apply more energy. That means you have to apply more energy to remove another electron. To remove second electron, you have to apply more energy. Again, similarly, to remove third electron, again you have to increase your energies. Are you getting my point? So from this, what we can say, first ionization energy of any element is less than its second ionization energy and third ionization energy. So it keeps on going on. So as you are keeping on removing electron from unipositive ion, or from a neutral atom to unipositive ion to double positive ion. So as you are removing electrons from what? From an element, what is going to happen? You have to supply huge amount of energy. That energy is called as what? Ionization energy. So from this, what we have understood, the successive ionization energies are increasing. Because why the successive ionization energy increases? Why I told you? Because as the electron is removing from an atom, from neutral gaseous atom to unipositive ion, from unipositive ion to double positive ion to triple positive ion, as electrons are increasing, are removing, so that there will be increase in effective nuclear charge. So due to increase in this effective nuclear charge, what is going to happen? You have to supply more energy to remove again one more electron. So due to that reason, the ionization energies are increasing, especially successive ionization energies. And in other terms also we can write the electron E by P ratio is decreasing. E by P ratio is decreasing. So due to this decrease in E by P ratio, number of electrons to proton ratio, as it decreases, so there will be increase in attraction. So when there will be more attraction of the electron towards its nucleus, then we have to apply, or we have to supply more energy, or we have to give more ionization energy. So hope you understood. So the concept of ionization energy. So in this case, very much important point, that is the factors on which this ionization energy is depending. So next we are going to see the factors on which ionization energy depends. So when you see this in these factors, there are certain factors like atomic radius. Second one is screening effect. Third one is nuclear charge. Then fourth one, very much important, that is stable electronic configuration. Stable electronic configuration. Fifth one is penetration power of orbitals. Penetration power of orbitals. In all these cases, one by one, we are going to see how this ionization energy values depends on these factors. Like when you compare the atomic radiuses, so as atomic radius is increasing, atomic radius when it increases while going down the group, when we go down the group, what is going to happen? Number of shells are increasing from one group, one period, one element to another element. Number of shells are increasing. As number of shells are increasing, what is going to happen? So the atomic radius is increasing. So as atomic radius is increasing, what are you going to observe here? As atomic radius is increasing, so automatically the distance from the nucleus to outermost shell, the distance from the nucleus to outermost shell is increasing. As distance from the nucleus to outermost shell is increasing, what are you going to observe? Here there will be decrease in effective nuclear charge because of screening effect. So There will be, due to increase in atomic radius, there will be decrease in effective nuclear charge. There will be decrease in effective nuclear charge. Due to this reason, what we can say that electron is loosely holded or loosely bounded with the nucleus, so that the electron can be easily removed with less ionization energy or with less supply of energy. So because of this reason, what we can say, as atomic radius is increasing, so what is going to happen? So there will be decrease in ionization energy. So ionization energy is inversely proportional to atomic radius. So from this what we understood, as number of shells are increasing while going down the group, so that number of shells are increasing, so that due to increasing number of shells, so there they will experience what? Nuclear force of attraction. Decrease in effective nuclear force of attraction or decrease in effective nuclear charge. So due to this decrease in effective nuclear charge because of screening effect, so we can say, what is that? We need very less energy to remove the electron. So from this what we can say, atomic radius is inversely proportional to ionization energy. So when it comes to screening effect, as I told you just now, so as number of shells are increasing, what is going to happen? So there will be electronic repulsions provided by inertial electrons. So these inertial electrons will provide repulsion. So to counter that repulsion, nucleus has to utilize much of its energy to counter that repulsion, so that the nuclear force of attraction will not reach to the outermost shell properly. So this is what called screening effect. So more is the screening effect. So obviously we need very less energy to remove that electron. So what is the point we are studying here? Ionization energy, where we are talking about, so how much of energy we are supplying to remove the electron. So if we are easily able to remove the electron, means we are what? Supplying less ionization energy. So this is what the condition. So next we are going to see nuclear charge. So nuclear charge means as atomic number is increasing. So atomic number means number of protons. Where the number of protons are going to go, it will go into the nucleus. So as more is the atomic number, so then what we can say, nuclear charge is increasing. So as nuclear charge is increasing, automatically it will hold the electrons very much strongly, so that you need much energy to remove the electron from the outermost shell. So because of that, nuclear charge is directly proportional to ionization energy. So the next important point that is we are going to study, that is stable electronic configuration. Stable electronic configuration. So when we can say that the electronic configuration is stable, so or the element is stable, when the electronic configuration is half filled or it is fully filled. When electronic configuration is, when we can say it is stable, when when the element's electronic configuration is half filled or either fully filled. Like we can say, how can you say that they are half filled or fully filled? For S subshell, we can say, generally we can consider for P. In P subshell, so how many electrons in p orbitals? It will be 6 electrons maximum. So when they are occupying 3 number of electrons, then we can say it is half filled. So when for D, so its number of electrons it can hold is 10 electrons. But when they are occupying 5 electrons, it is called half filled. Then similar F, its capacity is 14 electrons. So when it is holding about 7, then we can say the orbital is half filled. Then similarly, then electronic configuration is half filled. When it is fully filled, as we know, when p orbital will occupy 6 electrons, d will occupy 10 electrons, and f will occupy 14 electrons. It will give them fully filled. Then what is the importance of this half filled and fully filled? So they are what? Stable electronic configurations. When they are half filled and fully filled, they are considered as highly stable. When they are highly stable, so we know that to remove electron from the stable compound or stable element, we have to apply huge amount of energy. So more is the stable, so more will be the ionization energy. Similarly, we can see penetration power of orbitals. What do you mean by penetration power of orbitals? Like as electrons are going to enter into S p, d, f orbitals. So from where to remove electron, so we have to apply more energy. As I told you, s and p orbitals or subshells, they are more nearer to the nucleus and they are experiencing more nuclear force of attraction. So especially to remove electron from the s and p, especially for these two, so we have to apply more ionization energy as compared to d and f. Why? So because, as I told you, the distance from the nucleus, it is decreasing. That is, s is more nearer than p, than d and f. So due to that reason, so it will be more ionization energy if you want to remove electron from s subshell, then p, then d, then f. So these are what the factors on which this ionization energy depends. So now we will see and we will move to understand. So this is what the general concept of what ionization energy. Now very much important in the form of examination, that is for JEE or NEET. So we can see that is what is the trends in groups and periods. So this is what very much important. So the trends in period we can see. In these periods, generally, in general, I'm writing, in general, ionization energy increases. It's a general. Why it increases in period? As I told you, while going along a period, what you are going to observe, there will be increase in effective nuclear charge. Yesterday itself I told you why while going across a period from left to right, so there is no increase in shells. And the electron, every time the electron is entering into the same shell, but atomic number is increasing. Atomic number means nuclear charge. That means the electron or the proton number, protons are entering into nucleus. So that effective nuclear charge increasing as there is no increase in shells. So due to that reason, so the nucleus will hold the electrons with much more force of attraction. So to remove electron from that outermost shell of a neutral gaseous atom, so we have to apply more energy while going along or while going across the period. Are you getting my point? So this is what the general. But what we are going to see, few exceptions we are going to see. Let's take for second period elements. For second period element. In this case, these are what? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. See, when it comes to this, as we are going along this period, what is going to happen? Actually, there should be what is that? There should be increase in ionization energy. There should be increase in ionization energy. But what you are going to observe, the exception in the case of when you write the electronic configuration, we can write outermost electronic configuration is 2s1. This is what 2 2s2. This is what 2p1. This is what 2p2. I'm just writing outermost electronic configuration. So in this case, this is what 2p3. This is what 2p4. This is what 2p5. This is what 2p6. Now you will see beryllium. It is what 2s2. I told you here stable electronic configuration when they are half filled or fully filled. Fully filled means s orbital has the capacity of 2 electrons, so it has fully filled in the case of beryllium. And also you can see in the case of nitrogen, so it is what 2p3. It is what half filled. Are you getting my point? And when you see in the case of noble gases, it is what 2p6. It is also completely filled p orbitals. Already we know these are noble gases and highly stable. Is it clear? So due to that reason, always remember in a particular period, noble gases will have highest ionization energy. Highest ionization energy. Noble gases in that respective period. But in this case, whole periodic table we can see in the first period itself between hydrogen and helium. So it is the first noble gas and it has the smallest size. So from this what we can say, to remove electron from this helium, it is highly impossible. We can say it is high amount of energy is necessary. So due to that reason, it is the highest ionization energy. Highest ionization energy in periodic table. In periodic table. But this neon is the highest ionization energy in that period. In that period. That is second period, the highest ionization energy will be noble gases. That is, in the second period, it is neon. So when it comes to the second period, you can see the exception beryllium and nitrogen. In this beryllium and nitrogen, what you are going to observe? In this beryllium, it is what? Fully filled, fully filled, while in the case of nitrogen, it is half filled. So these are more stable, so that their ionization energies are just more than their preceding element, their succeeding element. So in this case, beryllium's ionization energy will be just more than boron, just more than boron. Similarly, nitrogen's ionization energy will be just more than oxygen. So in this case, what we can see, the final one we can write lithium, then boron, then beryllium, then carbon, then oxygen, then nitrogen, then fluorine, then neon. This is what the correct order of ionization energy values. Are you getting my point? So this is for second period. Similarly, we can write for third period elements. Similarly, we can write for third period elements. Like we can say sodium, magnesium, aluminium. What we can say? Silicon, phosphorus, sulfur. Then we can say chlorine, argon. So in this case also, generally we can see what is that? Aluminium. If you write the electronic configuration, so it is what? Between magnesium and aluminium. This is what 3s1. This is what 3s2. Fully filled. This is what? Fully filled. Then this is what? 3p1, 3p2, 3p3. Similarly for phosphorus, 3p4, 3p5, 3p6. It is highly stable. So in this case, we can see there will be alteration, that is magnesium, because since it is fully filled, it is fully filled and it is half filled. So they are highly stable. They are highly stable. So due to this stability, what we can say, the ionization energy will increase, because to remove that electron, it will be highly difficult. So there will be just what we can say, reversing the trend. That means what we can say, the previous element will go to the first. So in this case, argon will be maximum. Are you getting my point? So this will be the trend for third period elements in this case. Similarly, we can see a regular observation also. We can see from strontium to, we can say strontium to, and what we can say rubidium, strontium, indium, and what we can say tin, antimony, tellurium, iodine, and xenon. So there will be regular trend. So completely increases while going along the period. Is it clear? So next we can say what will happen in the groups. So what is the trend in groups? While going in groups, what you are going to observe is, while going along the group, the ionization energy decreases. Why the ionization energy decreases while going down the group? So as I told you, the number of shells are increasing. While going down the group, number of shells are increasing. So due to increase in this number of shells, as I told you, the element's atomic number is also increasing. Atomic number means the nuclear charge is also increasing, and with respect to that, the screening effect is also increasing. So as number of shells are increasing, the inertial electrons will screen the nucleus. So due to that reason, what is going to happen? The nuclear force of attraction will not reach to the outermost shell electrons, because due to increase in screening effect. So here two conditions are coming. One is atomic number is increasing. So as atomic number increases, nuclear charge increases. And similarly, as number of shells are increasing, so the screening effect is increasing. So there will be tussle between screening effect and effective nuclear charge or nuclear charge. So here, what is going to happen? Screening effect will be more prominent in the case of groups, by cancelling the nuclear charge. So due to that reason, effective nuclear charge is decreasing while going down the group and atomic radius is increasing. So due to this decrease in effective nuclear charge, what we can say, the nuclear force of attraction is unable to reach to the outermost shell electrons. So because of that reason, so that ionization energy is decreasing, so that we can easily remove the electron. Getting the point? So when it comes to group 1 elements like lithium, sodium, potassium, rubidium, and cesium. So cesium will be the least ionization energy, and more ionization energy will be for lithium. So why the cesium is having least ionization energy? Because of more number of shells and more screening effect. And in the periodic table itself, what is that? Lowest ionization energy. Cesium will be the lowest ionization energy in the periodic table. Hope you are getting my point. This is for group 1 elements. Similarly, we will see for group 2 elements. So, in this group 2 elements, what you can see, like beryllium, magnesium, and calcium, strontium, barium. So, here also you are going to see the same trend. But here we will have some exceptions related to, we can say, group 13 elements. What is that? Group 13 elements. In this group 13 elements, who are there? Boron, you can say. In group 13 elements, boron, aluminium, gallium, and indium, and thallium. So, boron, aluminium, gallium, indium, and thallium. So, these are the elements which are present. So, in this case, when you see there, what we can say, ionization energy, so that there will be difference in their ionization energies. When it comes to this thallium, it will undergo lanthanoid contraction. Due to lanthanoid contraction, by poor screening effect of 4f electrons, so the size of this thallium is decreasing so much. So when the size of the thallium is decreasing so much, what is going to happen? So obviously, it's what we can say, its effective nuclear charge is increasing. So due to increase in effective nuclear charge, it is highly difficult for the what to remove the electron from the outermost shell of thallium. So the thallium will show more ionization energy as compared to all these three elements. So who will have more ionization energy in this case? Boron. Then next will come thallium. Because of lanthanoid contraction. Why this lanthanoid contraction is happening? So because of poor screening effect of 4f electrons. And then next comes gallium. So even gallium will be more than aluminium because of transition contraction. This is because of lanthanoid contraction, and this gallium will show, what is that? Transition contraction. And next will come, what is that? Indium. Indium will also show the same thing. And finally at end, who will come? That is what? Aluminium. Are you getting my point? So this is what the exception which is shown by group 13 elements. Where you can see boron is having more ionization energy, but thallium being at the end, because containing it is having more number of shells as compared to all other elements, still it is having what? More ionization energy because of lanthanoid contraction. So this is what, and when gallium is also more than aluminium, ionization energy of gallium is also more than aluminium because it will have what? Transition contraction. Transition contraction is due to poor screening effect of 3D electrons. While lanthanoid contraction is because of poor screening effect of 4f electrons. So due to this reason, group 13 will show. Similarly, group 14 elements, when it comes to tin and lead. So tin is what's called, lead is coming after tin. So lead contains more number of shells. But still it is having more ionization energy than tin because of, again, same reason, lanthanoid contraction. So this is what happening in groups and periods. Then we will see how this ionization energy is varying in the case of transition elements. In the case of transition elements. See, when you see for transition elements or D block elements, in this case, while going along a period, like it will decreases. Sorry, it increases. Ionization energy increases, but there will be sudden jump when you go from copper to zinc, and similarly silver to cadmium, from silver to cadmium, and gold to what is that called? Mercury. So there will be sudden jump in the values or increase in this ionization energy values when you're going from copper to zinc, silver to cadmium, and gold to mercury. In this case, why there is sudden jump? Because there is increase in what we can say due to fully filled electrons. Fully filled electrons or fully filled orbitals, we can say. When it comes to zinc, 3d10, it is 4d10, it is what? 5d10. So this is what the reason for sudden jump in this case. And also for transition elements, we can see for third series, 3d series, when you see the 3d series elements, 3d series means what? It will start from scandium to zinc. 3d series means scandium to zinc. Similarly, you can write 4D series means what is that called? Yttrium to cadmium. Similarly, 5D series means we can write lanthanum. 5D series means it was starting from lanthanum to what we can say mercury. So, in this case of 3D series and 4D series, between 3D series and 4D series, the ionization energy values, first ionization energy values will be similar. Hope you're understanding. So, 3D series and 4D series elements, what we can say, their first ionization energy values are getting similar. Why there is similarity in what? We can say there is similarity in first ionization energy because of transition contraction. What is that? Transition contraction. Because of poor screening of electrons of 3D electrons. Poor screening effect of 3D electrons, they will show transition contraction. But when it comes to 4D series and 5D series, so 5D series elements will have more ionization than 4D series. 5D series elements, this 5D series elements, that is from lanthanum to, you can say, mercury. So they are showing what is that? The elements between this lanthanum to mercury I am talking about, between this. So this 5D series elements will have more than 4D because they are coming after feeding 4f electrons. That means they are showing what? Lanthanoid contraction. Lanthanoid contraction. Due to this lanthanoid contraction, what is going to happen? The size of the atom decreases, so that effective nuclear charge increases. Because of that reason, what we can say, 5D series elements will have more ionization energy as compared to 4D series elements. Like we can see in comparison with zirconium and hafnium. This is 4D series, this is 5D series. So this hafnium will have more ionization energy than zirconium. Hope you are getting my point. So this is the point we have understood. And also we can see between we can see silver and cadmium. What we can see, it is between like palladium and silver. We can see electronic configuration between. So next point will continue. So when it comes to first, we'll compare the ionization energies of what we can say first ionization energy and second ionization energies. So how will you compare this first ionization energy and second ionization energy? Like let's compare between group 1 and group 2 elements. From group 1 elements I have taken sodium, and from group 2 elements I have taken magnesium. Is it clear? So we will compare the first ionization energy and second ionization energy. So in this case, for group 1 elements, the sodium, if it will lose one electron. So first we will write the electronic configuration. What is the electronic configuration? Atomic number is 11. So we can write 1s2, 2s2, 2p6 and 3s1. For magnesium we can write 1s2, 2s2, 2p6, 3s2. In both these electronic configuration we will see, when we will observe, here we are going to see the outermost electronic configuration is 3s1, here it is 3s2. In this 3s2, it is what? Fully filled. Fully filled. If you want to remove one electron from this magnesium, you have to apply ionization energy and you have removed the electron, that is, it will become what? Mg plus. Similarly, you have removed one electron from sodium, also you have applied first ionization energy and sodium become Na plus. Are you getting my point? But when you compare first ionization energies of sodium and magnesium, you are going to see the electron is removed from the fully filled orbital in the case of magnesium. So here you have to apply more energy because fully filled means they are stable. When it comes to sodium, it is just 3s1, so we can remove electron and we are applied energy, that is called plus IE1. Is it clear? So in this case, the first ionization energy of sodium is less than first ionization energy of magnesium. Hope you understood this. Is it clear? And now what is the electronic configuration become? 1s2, 2s2, 2p6. Because one electron is gone, it is 2p6. But when it comes to magnesium, 1s2, 2s2, 2p6, 3s1. Now you see the electronic configurations of Na plus and Mg plus. In this case of 2p6, in this case of Na plus, you can see it is what? 2p6. 2p6 means fully filled. It is fully filled means highly stable. When it is highly stable means to remove one more electron from this Na plus unipositive cation. So you have to apply second ionization energy, which is higher always because it is highly stable. So that's why you have to apply more energy. So in this case, to become Na2 plus, we have added second ionization energy. And in this case again it is what? 3s1. It is easy to remove. So we have removed one more electron, so IE2 and Mg2 plus will become. So now what you can observe, the second ionization energy of sodium and second ionization energy of magnesium. Here second ionization energy, the electron is removed from fully filled electronic configuration. So it's highly stable. So we have to apply more energy. That's why second ionization energy of sodium is more than second ionization energy of magnesium. So in this case, what we can understand is, first ionization energy of group 1 elements is lesser than group 2 elements. But second ionization energy for what? Group 1 element is more than group 2 elements. So this is what we have understood from this first and second ionization energies. But when you compare, see, when we are comparing different elements, their first and second and third ionization energies, or for different group elements, then we can consider what is that? Their electronic configurations. Is it clear? But when you are seeing from, when the electron is successive, electrons are removed from the same element, we should not consider their ionization energies. One example we can write nitrogen. So its electronic configuration, we should not consider the electronic configuration. If you remove one more electron, so you have to apply energy, that is IE1, so it is becoming N minus. If you want to remove one more electron, you have to apply second ionization energy and it will become what? N2 minus. If you want to remove one more electron, so what we can say? Sorry, N removing electron, so it will become N plus, 2 plus. This was N3 plus. So what will becoming it is? I think this what? So it's becoming what? IE3. So here, when you write the electronic configuration, it will become what? Stable electronic configuration. So we should not consider stable electronic configuration when you are removing electron from the same element, this is what important point you have to understand. So this is all about ionization energies. Is it clear? And what is the trend in groups and periods we have understood, and what is their electronic configurations when it comes to first ionization energy and second ionization energy, for which element, and how to consider their first ionization energy and second ionization energy values, especially by considering their electronic configuration. We have to check whether it is fully filled or half filled. Is it clear? And when they are fully filled and half filled, they are highly stable. So to remove electron from those kind of elements, we have to apply more energy. So this is what about the concepts related to this ionization energy. And also we will practice questions based on this atomic radius as well as ionization energies, and any more important points which are there through questions we will practice. Thank you all.